Okay, I want to carry on going over this practice test. I'm going to try to finish out the multiple choice in this video, and then I'll make a separate video for free response. Number 7, 3 samples of 1.12 grams, 1.8 grams, and 1.562 grams are mixed together. The combined mass of the 3 samples expressed to the correct number of significant figures would be recorded as. Again, we have to realize, what are we doing? Are we doing adding, subtracting rules or multiplication, division rules for significant figures? We're doing adding, subtracting because we're mixing stuff together. Okay, so we have 1.12 grams. We have 1.8 grams. And we have 1.562 grams. Okay. And then I go to the least precise measurement. This is the hundredth place. This is the tenths in 1.8, and this is the thousandths. So I'm going to report my answer to the tenth place when I add them. Okay. So on my calculator, I get 1.12 plus 1.8 plus 1.562 equals, and I get 4.482 grams. Okay, I have to report my answer to the tenth place because of the 1.8 gram measurement. Since this is greater than 5, I'm going to round that up to 4.5 grams. So the best answer is D, 4.5 grams. Don't be falling into this trap of 4.4. Okay, D is the answer to number 7. Okay, when 5.7 meters is divided by 2 seconds, the quotient is correctly reported as, okay, multiplication, division. Here's division. So we count sig figs in each and report our answer to the one that has the fewest. 5.7 meters is 2 sig figs. That's 1 sig fig. Our answer better have 1 sig fig. That's D, 3 meters per second. Product of 7, that's multiplication, of 13 and 5.7 is correctly reported as, okay, again, this is 2 sig figs, 2 sig figs. Answer has 2 sig figs. Okay, I can already see before I multiply, it's either going to be 74 or 75. So I'm going to punch that in my calculator. 13 times 5.7 is 74.1. So that rounds down to 74. Okay. All right. What is 1.245633,501 times 10 to the 8th rounded to 4 significant figures? Remember, the 10 to the 8th doesn't really do anything to our significant figures, even though that's part of the number. The number of significant figures is that appears before the 10 to the in the scientific notation. So just go back to the first 4 significant digits. 1, 2, 3, 4, and it's just going to be 1.245. And then I got to round up. See that 6? 1.246 times 10 to the 8th. Doesn't affect the 10 to the 8th part at all, right? The number's still got to be roughly the same number. Okay? They would have been more devious if they had 1.245 and 1.246 as possible, times 10 to the 8th as possible answers. Okay? All right. So the answer is C. Now, number 11 is tricky because you have both multiplication and addition. So you need to use your order of operation understanding, and then you need to use your significant figures understanding. So when you have addition and multiplication, the rule is multiplication first for order of operation. That's just from your math class. That's a convention. So for multiplication, we have to count the number of sig figs at each. 4 sig figs. 3 sig figs. Answer better have 3 sig figs. So I'm going to write equals, and I'm doing 3.475 times 1.97. And I get 6.84575. So I've got to round that to 3 significant figures, which is 6.85. Okay. Plus 2.4712. Now, I don't even have to do this calculation, but that has 3 sig figs, okay, and it's the hundredths place. And then I go from here, this is the tenths, hundredths, thousands, 10,000s. So my answer better have the hundredths place in it, so it's going to be 3 significant figures. Okay, be careful, because if that sum is more than 10, it could have 4 significant figures. So let's make sure we do this all the way through. The best thing that you can always do is just do the whole problem. If that was 6.85 plus 6.85 something something something, you'd still have to record it to the hundredths place, in which case you'd have more than 3 significant figures. So let's just add it up to be sure. Okay, and the rule is hundredths for addition, more than the hundredths, provide your answer to the hundredths. You see, if this number here, if that was bigger than 10, you'd still have to report it to the hundredths place, so you'd have like 10.3 something, whatever, if you were adding 3.4712. So that would have been a better example, which could have shown a common mistake. All right, so 3 sig figs, the correct answer would be 9.32. All right, how many significant digits should be shown in the product of 1.6 and 2.4? 1.6 centimeters, 2.4 centimeters, 2 sig figs, multiplication, 2 sig figs. Answer better have 2 sig figs. Okay, that one was pretty straightforward. Next one. How is the measurement 0.000065 centimeters written in scientific notation? Again, in scientific notation, I have to have a number between 1 and 9 point something times 10 to the something. So again, I'm going to move this decimal place forward 1, 2, 3, 4, 5 places. And so it's going to be 6.5 times 10 to the minus, because it's less than 1, 5. Which of the following best describes temperature? Remember, temperature, we said, is kind of related to the average kinetic energy of the molecules, and the average kinetic energy is the kinetic energy of any moving object is 1/2 its mass times its speed squared. So the best answer is B. Okay, it's just a measure of the average kinetic energy of the particles. Okay. How is a Celsius temperature reading converted to a Kelvin? You just add 273.15. Okay. Just remember, 0 degrees C is equal to 273 Kelvin. How do you get from one to the other? Add 273. Remember, there's no negatives on the Kelvin scale. Energy is measured in units of joules. Okay. Mass is grams, pounds is a force, and Kelvin is a temperature. If a piece of aluminum is heated from 30 to 50, what is the value of delta T? Delta, remember, just means change in. So delta T equals T final minus T initial equals 50.0 degrees C minus 30.0 degrees C. and that equals 20.0 degrees C. Okay? B, or 20.0 Kelvin. Remember, delta T is the same in Kelvin or in degrees C, and that's because a difference in degrees C is the same as a difference in Kelvin, because every temperature on the Kelvin scale is 273 more than the degree C scale. 18. A 4-gram sample of iron was heated from 0 to 20. It absorbed 35.2 joules of energy as heat. What is the specific heat of this piece of iron? Okay, so heat Q absorbed from a sample is equal to its specific heat times its mass times the change in temperature. And it says, read the question carefully, what is, for what it's asking, what is the specific heat? So you're trying to find S here. You're solving for S. Okay. It absorbed 35.2 joules. That's the heat. So that's 35.2 joules is equal to the specific heat times the mass, 4 grams, times delta T. Delta T, it heated from 0 to 20, so that means the temperature increase was a positive 20, so it's 20 minus 0. I'm going to leave the units out only because I'm out of space here, so do that on your test. Okay, so I'm going to divide each side to get S by 20 times 4, which is 80. So 35.2 divided by 80 is 0.44, and the units are joules per gram degree C, D. One thing that you could really use kind of common sense for this without even doing the calculation, if this was a multiple choice or standardized test of some form. You know the specific heat of water is 4.18 joules per gram degree C. And we know that metals are much better conductors than water, and we know that good conductors have low specific heats. 2.27 is a pretty significantly high specific heat, and most metals have specific heats of less than 1. So, you know, you could use that sort of reasoning, even if your calculation wasn't going well. 19. The quantity of energy released or absorbed as heat during a chemical reaction is called, that's just called the enthalpy of reaction, or the heat of reaction. Okay, temperature is temperature. Entropy, we didn't even talk about yet, so you don't need to worry about that. And free energy, same thing. Heat of reaction, enthalpy of reaction, same thing. Okay, in an endothermic reaction, 20. In an endothermic reaction, the total energy at the beginning of the reaction is, okay, so endothermic means I have to put heat in. So this is 20 over here. Okay, that means I start at a lower energy, and I have to put energy in. The surroundings provide energy in order for the reaction to occur. So you start here at a low energy, and you are absorbed to finish at a high energy. So the chemical or physical change in this case is a reaction, so it's a chemical change. Takes energy in from the surrounding. Okay, so that means the total energy at the beginning of the reaction is less than the total energy at the end of the reaction. The surroundings would decrease in temperature here. 21. Ice melting is an example of, okay, do you have to put energy in for ice to melt, or does energy get released for ice to melt? You have to ask, which is higher in energy? Ice at 0 to water at 0. Well, you have to add energy in to separate the molecules from each other to allow them to move past one another. That means ice is lower in energy than water. That means it looks just like number 20. Ice starts here, water is here. Even though they're at the same temperature, they're at different energies. It's an endothermic process. Okay. We'll do the free response on a separate video.